Hey everyone, welcome back to Dietitians and Nutrition Support. Today we're going to be talking about the digestion and absorption of our third macronutrient, lipids, otherwise known as fats. Lipids are really interesting because they're actually a diverse class of nutrients. So there's a couple different types of lipids that we're going to see, and all of them are kind of categorized as generally being insoluble in water. So there are three primary types of lipids that you're going to see found in food as well as in our bodies and cells and tissues and things like that. The first kind and the most abundantly seen is triglycerides. Next you'll see phospholipids, and third is sterols. Okay, so let's first talk about triglycerides. These are most abundantly found in our diet as compared to any other type of lipid, so they're really important for us. Triglycerides are called that because they have three different types of fatty acids that come off of a glycerol backbone, or the glyceride part of triglyceride. The three fatty acids that come off of the glycerol will actually help for us to describe what kind of fat it is. We'll also call that kind of fat, the combined triglyceride, a fatty acid as well. So it gets a little bit confusing, but I promise for the most part we're talking about either free fatty acids or a fatty acid, which is typically a triglyceride. The big fatty acids, the triglyceride fatty acids, can also be described using different features of themselves. So you might be able to describe some characteristics or even some nomenclature of fatty acid based on the length of the chain, so how long the free fatty acids are that are attached to the glycerol backbone, as well as the shape or the configuration of the fat, and also the saturation as to whether or not there's double bonds. So let's talk about that triglyceride chain length. So first, you could have short chain fatty acids, which are pretty much any fatty acid under 6 carbon atoms, so meaning 6 chain lengths. Medium chain fatty acid is going to be somewhere between 6 and 12, and a long chain fatty acid is going to be somewhere over 14. Short and medium chain fatty acids are more likely to get broken down and absorbed as well as metabolized faster than long chain fatty acids. For this reason, we don't really see them being stored as adipose tissue, whereas we might see longer chain fatty acids being stored in the body as well as being utilized. In general, long-chain fatty acids are just more abundant in nature, meaning that when we're trying to consume foods, we're typically going to be consuming more long-chain fatty acids than we are short or medium-chain fatty acids. So the next thing to consider with triglycerides is saturation. And what we're really thinking about here is whether or not all of the fatty acids that are coming off of the glycerol backbone are fully saturated with hydrogens. If they are fully saturated with hydrogens or are a quote-unquote saturated fat, that means there's no double bonds at any point within any of the fatty acids. If you were to have one double bond within one of the fatty acids, then you would have a monounsaturated fatty acid, or a MUFA. And if you were to have more than one double bond present within the fatty acids, then you would have a polyunsaturated fatty acid, or a PUFA. So the saturation level of a triglyceride actually impacts what the physical features are going to be. So if you have a saturated fatty acid, because the saturated fats don't have any double bonds to cause any disturbances in the way that the chain lengths of the fatty acids lay, it means that the fatty acids within the molecule as well as next to other molecules of fat can go very closely together and can kind of pack in there just based on the configuration of the lipids. This means that if you have a saturated fat, it is more likely to be solid at room temperature. So some examples of saturated fats are things like butter or coconut oil. Now for thinking about unsaturated fatty acids, those unsaturated fatty acids will include a double bond, and double bonds can make it so that you can't have a completely straight fatty acid, so you're going to see a few different kinks or the change in configuration of the shaping of the fatty acid because it's unsaturated. Now with that change in configuration, we'll see that the fatty acid is no longer able to nestle really close next to other molecules of fatty acid, meaning they're going to have to be spread a little bit further apart, which is why we see that unsaturated fatty acids are more likely to be liquid at room temperature. And an example of that would be something like olive oil or canola oil. So right alongside this idea of saturation is the idea of hydrogenation. You've probably heard of trans fats before, and trans fats are actually a produced type of fat. They are produced through the process of hydrogenation, in which you take an unsaturated fat, such as a canola oil or something like that, and you hydrogenate it. You add extra hydrogens to it to take it from being an unsaturated fat in a cis conformation to adding the hydrogens and turning it into a trans conformation, which will allow for it to be able to nestle closer together, just like a different kind of saturated fat would, so that you can have a solid fat product. People will make trans fat, or also known as hydrogenated oils, because it helps to reduce rancidity and oxidation of the lipid product, and it also promotes a longer shelf life. But what we found with these trans fats is that they're not actually healthy for humans to be consuming in large quantities or quantities at all. The recommended intake is as little as possible and hopefully zero intake of trans fats. So we've actually seen bans on products containing trans fats that started in 2018. So we're not supposed to see any trans fats anymore in products that we purchase. You will see some naturally contained trans fats that are in meat products, but for the most part, we don't really have a lot of these man-made trans fats in our diet anymore. So we also have 2 essential fatty acids, or EFAs, that we have to consume because our body does not create them naturally on its own. These 2 essential fatty acids include omega-3s, alpha-linolenic acid, and omega-6, linoleic acid. Omega-3 fatty acids can be found in foods like walnuts, soy, and flaxseed. Omega-3s are particularly important because they can be transformed into eicosapentaenoic acid, or EPA, as well as docosahexaenoic acid, or DHA. EPA and DHA are both super important for things like brain development as well as inflammation in the body. We also know that EPA and DHA can be consumed directly in things like fish oil. Our omega-6 fatty acids can be found in things like vegetables as well as nut oils. So we've spoken a lot about triglycerides so far, but let's talk about the other kinds of lipids we can also see. So phospholipids can also be contained in the diet, and we also make these in the body. So these are not something that we have to consume. Our body can make them. They're made up of a glycerol backbone with 2 free fatty acids attached to it, as well as a head group that contains a phosphate. So this phosphate head group is actually really interesting about phospholipids because it allows for part of them to be hydrophilic. So the phosphate head group actually likes water, and it allows for the entire phospholipid to become soluble in water, whereas the free fatty acid end of it, or the 2 tails coming off the phosphate head group, are considered to be hydrophobic, just like we would consider most fats to be, that they don't like water. This is a really important feature of the phospholipid, and it's why the phospholipid is so useful for things like cell membranes, as well as micelles and chylomicrons, which we'll talk about shortly. We also have sterols, which you might think of cholesterol as being probably the most prevalent sterol that we have heard of. Sterols contain multiple rings of carbon chains, and you can see plant sterols, or sterols derived from plant products, as well as cholesterol, which is what we'll see consumed in animal products, as well as what we as animals, humans, will create endogenously or inside the body. You do not need to consume cholesterol. Our body can make it on its own, but if you do consume cholesterol, your body can also utilize that. The most important things that cholesterol does in the body is the synthesis of hormones, vitamin D, and bile salts. So how much lipid do we actually need? While the acceptable macronutrient distribution range for lipids is quite wide, it's actually 20 to 35% of total daily calories. We also have recommendations to minimize saturated fat intake below 10% of total daily calories, and to reduce trans fat intake as close to 0 as possible. And we also have adequate intake values for both our omega-3 and our omega-6 fatty acids, which again are those essential fatty acids. So we've talked a lot about the different types of fats that we might have in our diet, but what actually happens when we consume them and then digest and absorb them? Well, let's jump to the other screen and take a peek. Okay, so let's start to talk through the digestion of lipids. The first thing that's going to happen is, of course, you're going to have your lipid, and it's going to go into the mouth. In the mouth, we will see two different types of digestion happening. The first type of digestion is that mechanical digestion, that mastication or chewing that's going to start to break down the physically large pieces of food into smaller pieces of food. There's a very small amount of enzymatic breakdown that's going to happen in the mouth, and that's going to happen from lingual lipase. So lingual, meaning it comes from the mouth and the tongue. And then lipase, this lip part, going to say something related to lipids, and the ase part, as you're probably familiar with, is indicating that it is an enzyme. So after we've done our little bit of chewing and had our little bit of lingual lipase activity on the triglycerides that we have consumed in our diet, of course we're going to see that person swallow, it's going to go down the esophagus, and it's going to go into the stomach. If we're thinking about digestion that happens in the stomach, we are actually not really going to see a lot of lipid digestion happening here. We know we have a really acidic environment in the stomach, but that's not really going to help us to break down the triglycerides that we still have. What is important is that when lipid gets into the stomach, it's going to stimulate the secretion of cholecystokinin. So we talked about cholecystokinin a little bit, CCK as it's also known, in our protein video. So we see both lipids and proteins helping to stimulate the release of this cholecystokinin from our various endocrine cells. So when this hormone, CCK, is released, we're going to see it do two things for us in terms of lipid digestion. The first thing that it's going to do is it's going to help stimulate bile release. This bile is going to be released from the gallbladder, but remember that the actual point of creation of bile is the liver. So we create it in the liver and we store it in the gallbladder. So when that CCK is coming around into the circulation, you're going to start to see the gallbladder say, okay, here is some bile that we're going to release, and it actually dumps that into the small intestine. The second thing that CCK is going to do for us is it is going to stimulate pancreatic enzymes to be released also into the small intestine. So then, as you can probably imagine, we don't really have too much actually happening in the stomach because all of these things are getting dumped into the small intestine. So let's talk about that. So as we have our bolus coming into the small intestine, we know that it still contains lipid in it, and it's going to contain them in the form of triglycerides. The first thing we have is our bile that's going to be interacting with our triglycerides. And what it's really going to do is it's going to take our fat, which is in the form of droplets. So we'll see these like large kind of globules of lipid traveling together throughout the digestive tract. And it's going to take these larger fat droplets and it's going to turn them into smaller droplets of triglyceride. And the other thing that our CCK is going to be stimulating is the release of those pancreatic enzymes. And in this case, we're talking about pancreatic lipase, which again makes sense. The source is the pancreas. We're talking about lipids, and it's an enzyme. The pancreatic lipase is going to be particularly important for the actual breakdown of our triglycerides. So remember, we've got a bunch of triglycerides, and these are going to be our glycerol backbone, and then it's going to have 3 fatty acids coming off of there. And so what the pancreatic lipase is going to do is it's going to help us cleave off 2 of the fatty acids so that it turns it into a free fatty acid, and then this glycerol with 1 fatty acid stuck on it, which is called a monoglyceride. So we have our 1 monoglyceride and then our 2 fatty acids that are coming from our single triglyceride broken down by pancreatic lipase. So you may be remembering that lipids are actually not water soluble. So when we have all these lipids just flowing through the system here, they're actually going to not just be hanging out willy-nilly, but they're going to try and organize themselves in a way that's suitable based on the fact that they are hydrophobic, meaning they don't like water. So this means when they're inside the lumen or still inside the digestive tract and they have not yet been absorbed into a cell or the enterocyte, we're going to try and organize all of these goodies into something called a micelle. So these micelles are going to be a formation of our free fatty acids and our monoacyl glycerols or monoglycerides. And it's going to take all of those and it's going to package them up so that they can move to the enterocyte. So let's check out the shape of this micelle here on the right. So micelles, because they're made of these free fatty acids and these monoacyl glycerols, what we're going to see is the usage of phospholipids to actually protect the micelle. So remember, phospholipids are going to have this hydrophilic head to them, and then they're going to have the hydrophobic tail. So they're going to start aligning themselves in these kind of spherical shapes to create a sort of spherical shell where on the inside you'll see all of our free fatty acids and monoacyl glycerols and those things that are hydrophobic and want to stay away from the water going towards the core. So this micelle will have our hydrophilic outside, hydrophobic core, and will help for all of these pieces of our lipids to move to the enterocyte so they can be absorbed. You'll also see some cholesterol in the core of our micelle as well. So really we see representation of all different types of fats. So this micelle formation is actually taking place all throughout this small intestine, and then we're going to see absorption of all of the pieces of the micelle. So when the micelle makes it to the enterocyte, you're actually going to see it disassemble itself so it can absorb all of the different components of the micelle into the enterocyte. And when it gets inside the enterocyte, we're going to see it face the same issue, the fact that for the most part our lipid pieces are hydrophobic and they don't really want to just be floating around in what is basically a bunch of water. We're going to see them reform in another way to make sure that they can have that protective hydrophilic outside and hydrophobic inside. So inside the enterocyte, that is going to be called a chylomicron. Okay, so let's check out this picture of a chylomicron. So chylomicrons, this inside of the cell formation of our lipids, they're going to be created just as we have already explained because the lipids do not want to just be floating around in water. So they look quite similar to our micelles. The first thing you'll notice that is similar is the outside here is going to be of those phospholipids. So with the hydrophilic side on the outside and the hydrophobic side on the inside. You're also going to see the content being similar with our cholesterol and triglycerides being on the inside portion here. And one thing that is a little different is you're going to see some embedded apolipoproteins. We're not going to go too much into those today, but just know that there's some proteins that are going to be on the surface of our chylomicron to help them form together. So now once we've made our chylomicrons in our enterocyte, we're going to have these chylomicrons. This is going to be our primary kind of structure of how lipids are going to be. But two, the second way that we might have some additional lipids still in our system, we might have some medium chain fatty acids. And we also might see some short chain fatty acids. These are going to be treated just a little bit differently here as we start to transition to absorption. So first, our chylomicrons are going to go directly into the lymphatic system, whereas our medium chain fatty acids and our short chain fatty acids, those are going to go, just like most of the things we absorbed or have seen in our other videos, they're going to the bloodstream. So throughout the lymphatic system, we're going to see our chylomicrons being transported all throughout the body. And what the chylomicrons are going to do is they're going to take all the lipids that we just consumed and they're going to provide them to cells that might need some lipid. At various locations, the cells throughout the body that need these lipids, you'll start to see the chylomicrons be acted on by something called lipoprotein lipase. This enzyme is also called LPL. When lipoprotein lipase acts on the chylomicrons, what we're going to see happen is it's going to grab off some of the triglycerides that are found in the inside core of our chylomicron to provide the triglycerides to various points. So we're going to keep seeing this process happen where the chylomicrons are going to be acted upon by lipoprotein lipase, which the lipoprotein lipase is going to keep pulling out triglycerides, pulling and pulling and pulling, until basically we're going to get to the point where we just have the outside shell of the chylomicron and the inside is going to be mostly cholesterol. This is what we call a chylomicron remnant. So this chylomicron is finally ready to leave the lymphatic system and it's going to head towards the liver. So at this point, the liver will then take our chylomicron remnant, it'll take all of the cholesterol that's from the inside, and it'll help to distribute all of that cholesterol and all the various pieces of the chylomicron to turn it into other lipoproteins. So these lipoproteins are things you might be familiar with, like low-density lipoprotein or high-density lipoprotein, which people also will call LDL or HDL. So those are probably very familiar measures of blood lipids that you've seen. So one just quick important thing to remember is that chylomicrons might be a lipoprotein, but when we're doing measurements of what actual blood lipid levels look like, chylomicron levels will only be high following a meal. So you have to have a meal to have chylomicrons form because they're coming from the enterocyte, they're made there. Whereas other lipoproteins like LDL and HDL are being consistently made and managed by the liver. So you'll always have some presence of them within your bloodstream, even if you didn't just have a meal. Okay, so let's take this all the way back to our actual digestion pieces here. So we already consumed our lipid, it went through the stomach, it went through the small intestine and did all of that chylomicron action and turned it into other lipoproteins and all of that good stuff. So what we have left over after we get through the small intestine and come into the large intestine should not be very much stuff. We should have really done a lot of breakdown and absorption of pretty much all of the lipid that we had in our diet. You might see minimal levels of excretion, but for the most part, you don't really want a whole bunch of lipid getting into the colon. Any small amounts of excess that you might have will, of course, be excreted. So you may be wondering, how does all of this information about digestion and absorption and lipids relate to how we actually practice nutrition support, or what we would do if you were a dietitian and needing to make some decisions about lipids? Well, let's talk through a couple of our interesting topics about lipids and what we might do with them. First up is medium-chain triglycerides, or medium-chain fatty acids. We might also see this called MCTs. MCTs, as we kind of spoke about before, are able to be absorbed from the enterocyte directly into the bloodstream. This makes them easier and more accessible than longer chain fatty acids. So these medium chain triglycerides can be really good for people who may have a little bit of difficulty with fat digestion and absorption. So when MCTs enter into the bloodstream, they're actually very quickly metabolized into ketones, which can be used as an energy source. This can be super helpful for people who are having difficulty with fat digestion and absorption. So these could be folks with malnutrition, with reduced bile production, those folks that are experiencing steatorrhea for some reason, lots of different reasons why you might want to be able to provide a little bit of extra energy from lipids that are quickly absorbed instead of the longer chains. The next thing to think about in terms of nutrition support is formulas that contain omega-3 and omega-6 fatty acids. Of course, we're always going to be providing those essential fatty acids in the necessary quantities in every single nutrition support formula or parenteral nutrition. But there are some formulas that are specifically formulated to have additional omegas in them because of the potential immune modulatory effects that help to reduce inflammation in the system. We've seen some literature presented that says that omegas and omega-3s in particular can help to reduce systemic inflammation in the system. So by providing additional omegas within nutrition support formulas, we hope that for our patients, specifically those in critical care and experiencing a lot of inflammation, can actually see a reduction in that inflammation based on the formula that they're provided. Fat content in the diet can also be important for issues like gastroparesis and nausea and vomiting. In terms of gastroparesis, we're thinking about when someone has gastric dysmotility, meaning they're having issues with their stomach actually emptying into their small intestine, even though they don't have any types of physical blockages. For people with gastroparesis, they can oftentimes struggle if they have an excessive amount of fat in their diet, or even what some would consider a high but normal quantity of fat within the diet. So for those people with gastroparesis, a recommendation to have lower fat intake is appropriate. For people with gastroparesis, medium chain triglycerides might be appropriate because, as we already spoke about, they're a little bit easier for folks to digest and absorb. The same thing can go for folks who are experiencing consistent nausea and vomiting. Sometimes a reduction of fat content within the diet can assist with that, as well as utilizing MCTs, because again, they don't rely on a lot of bile salt production, and they don't really rely on all of the same things that the longer chain fatty acids need to be broken down, absorbed, and then distributed through the body. For people who are struggling with fat intake as well as potentially general calorie intake, you might see improvements if they're able to have lipids in a liquid form. This could be things like nutritional supplements or milkshakes, as opposed to them trying to eat fried foods or other really fatty foods. One last thing to consider for fat intake for those experiencing nutrition support is what would we do for folks who are on a blenderized tube feeding protocol. If they're making their own blenderized tube feed, you might recommend for them to use fat sources such as canola oil, extra virgin olive oil. They'll get fats from any meats that are added to their blenderized tube feed, and you'll also see dairy products, cream, nut butters, and things like that being appropriate sources of lipid in a blenderized tube feed. While this was a lot of different information on what lipids look like, from just their physical structure to how they're digested and absorbed in the system, hopefully this gave you a really good introduction as to how this pertains to nutrition support. And if you're interested in any more information about lipids and nutrition support, we actually have a 4-part lipid series of videos that you can view that talk about some different ideas related to new lipid products that are available on the market for dietitians working in the U.S. We hope this video was helpful, and if you have any questions or comments, please don't forget to leave them in the comments boxes below. We look forward to seeing you next time.